Okay, let's go blue. Okay, we're talking about water here. A pebble is dropped into a calm pond, causing ripples to form in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what is the rate of the total area of the disturbed water changing? At what rate? All right, so all right, we've got a circle that looks terrible, and we're dropping the pebble in, and so the circle is increasing because this radius is increasing. All right, that looks wonderful. It's a potato, and so we know the formula for the area of a circle. All right, the area of a circle, you've known that for a long, long, long time, is pi r squared. All right. All right, and we're given that the radius of the outer ripple, the very first thing that was created there, is increasing at a constant rate of 1 foot per second. Well, that's dr dt. So we are told that dr dt is 1 foot per second. Okay, good. And it's asking us to find then at what rate is the area of the disturbed water changing. So this area here. All right. So we want to know what dA dt is. All right. And watch my little notation here. dA dt when the radius is 4 feet. Okay. So that little thing right there, because I don't have function notation on these, and it makes sense that we don't because of the extra variable that's floating around. So we have to kind of use this the fractional notation to do these. All right, you don't want to put an a prime and an r prime and all that stuff whenever your variable is t. You just don't want to do that. All right, you never see that. All right, so here we go. So the very first thing I want to do, there's two things I want to do. The first thing I want to do is I want to take the derivative of this with respect to time, because that's exactly what we're trying to find. So dA dt, all right, will equal 2 pi r, oh my gosh, the circumference, that is not a coincidence, and then times dr dt. Okay, and then the next thing to do then is to substitute in. All right, now sometimes they're going to be asking you to solve for things on the right-hand side, but not this time. So this time we wanted to find out what this was equal to when the radius was 4. Well, when the radius was 4, we also had this, we knew that the radius was changing at 1 foot per second because it's always doing that. All right, so that didn't change with time. That was a constant, but that's okay. We still have to use it. All right, so number 2 then, part 2, is to substitute in. All right, so dA dt at that particular moment, yeah, is going to equal 2 times pi times, and the radius was 4, right? And dr dt was, look, I'll just go ahead and put it 4 feet, right? And then the radius, dr dt was, the radius was changing at 1 foot per second. And that just kind of keeps up with all the units and everything. And so what we got here, 2 times 4 times 8 pi, and the units just work out perfectly, square feet per second. Oh my gosh, I love it. I love it. Yep. So at that moment, now that's going to change depending on your radius, right? And that makes sense because as the circle gets larger, there's more and more area that's being created. All right, and so as more and more area is being created, that area then has to change at a greater rate. Makes total sense. All right, that was example